Okay, so a couple more examples and going through this application of vectors. And part of this is going to look at what happens if you want to go into the third dimension for vectors, and then using vectors to kind of calculate work in a very, again, very basic and prime, I guess, elementary way to represent that work. And again, if you've been in a physics class, this is going to be very simplified, compared to that. So. Well, first thing, 3D. The nice thing about the third dimension is that everything and every formula and every relationship that we know in 2D also works in 3D. So, I think I maybe referenced this just a bit in the very first video. But if you have a two-dimensional vector, we know there's a I component, a j component. But then for a three-dimensional vector, there's an I component, a j component, and then also a k component for that third component, kind of coming off the page, if you will, and breaking into that third dimension. If you're talking about just letters, there's like x would be like with the I. If you're talking about like on a coordinate plane, the y would be with the j, and then your z, which is that third dimension, would be for your k. And again, just starting to get used to the language. I, j, and k, not joking, not that funny. I, j, and k would indicate you're dealing with a vector. X, Y, Z, you'd be dealing with a point. Okay. So, for example, 10, 11, 0, I could call that a point with an X, a Y, and a Z. But if I wanted to describe a vector that connected this point to that point, I would need an I and a J and a K. And really, you're just looking at how do you get from point A to point B. So in terms of like the X component, so going from 1 to up to 10, I'm increasing it by 9. And so then I would represent that as a vector of 9 in this direction, in that I direction. So then I say, okay, 9I. And then to get from negative 12 to 11, that's down 23 in that J direction. So minus 23J. And then to get from negative 4 up to 0, I would say plus 4K. So here's a vector, again, that would get you from point A to point B. And remember, it's a position vector. It tells you how to get from the first position to the second position. Okay, now I see a formula here for example 2 to find magnitude. Find the magnitude of this vector. And it works just like two dimension, except for you add one more dimension to that formula. So the magnitude of V would start off by saying, okay, that's the square root of negative 2 squared plus 3 squared plus 8 squared. So I'm just adding this third dimension in terms of, or this third component, I should say, when I'm dealing with a third dimensional vector. Notice there are no i's, no j's, no k's, and therefore this is no longer a vector, it's a scalar. And so then I'd say, okay, let's simplify. That's the square root of 4 plus 9 plus 64, 68, 77, I think, if I did that right. 13, yeah, 77, which is no perfect squares in it. So we can leave it like that. Okay. Now, finding distance between these 2 points is the distance formula, just extend it to one more dimension. So the distance formula, one way to think about this is to think about, okay, 4 minus negative 1 squared plus 5 minus 0 squared plus negative 7 minus 3 squared. So now I have the Pythagorean theorem, just extended the third dimension. Okay, so square root of 25 plus another 25. Well, that's nice. And then that's, 10, so 100. Very nice. So it's the square root of 150. And if you want to simplify that, you realize that is 25 times 6. So that is 5 root 6. Now, if I had actually thought about this from a vector component or vector perspective, I could have thought, okay, how do I get from 4 to negative 1? I'd go down 5, so negative 5i. How do I get from 5 to 0? I go down 5 as well, so 5j. How do I go from negative 7 to 3? I actually go up 10, so 10 in the k. And then this position vector, I could just call this like vector v. And if I found the magnitude of vector v, notice I'd be doing the exact same calculation. So you could also think about it from that perspective, that you could just find the magnitude of that vector, which is still equal to square root of 150 or 5 root 6. So either way, you get that same answer. Okay. Okay, yeah, angle between two vectors. The formula in 2-dimensional is the same as the formula in 3 dimensions. So we still have cosine of theta is equal to the dot product of the two vectors divided by the product of their magnitudes. And for our dot product, which will be the top part of this ratio, in 2 dimensions, we focus on the I component times the I component, and then the j component times the j component. Well, we'll just add on the k component and the k component. So we do 1 times 2 plus 1 times 6 plus negative 3 times 1. So then I take that, I divide it by the magnitude of u and magnitude of v, or in this case, I guess v and w, or whatever you call it. So the square root of 1 squared plus 1 squared plus negative 3 squared. So I feel like I'm extra messy today in my handwriting. I apologize. Divided by 2 squared plus 6 squared plus 1 squared. Okay, so remember, that's what cosine of theta is. So cosine of theta equals 2 plus 6 is 8, minus 3 is 5, divided by the square root of 1 plus 1 is 2, plus 9 is 11. And again, if I make any mistakes, send me an email or put in the comments. 9, 10, 11, okay, times the square root of 4 plus 36 is 40 times, or plus 1 is 41. And again, I don't really have to do any kind of simplifying because I'm just going to inverse cosine this. So theta is equal to the inverse cosine of 5 divided by root 11 times root 41. And I know that this is a positive ratio, so I already know it's going to be an acute angle. So again, didn't learn from my first example. I should have typed these out before, but that's okay. So 5 divided by the product of the square root. There it is, the square root of 11, and then times, there it is, square root of 41. And again, I'm in degree mode just because, again, I think we have a better intuitive feel for that measurement. 0.382 degrees. Okay, excellent. So again, anything that happened in the second dimension will also happen in the third dimension. Okay, so now the last two examples, we're back to 2 dimensions because I only see an I and a J. I only see an I and a J in a 2 ordered pair for your coordinate, not an ordered triple. So this is going to be our model for work. And again, very, very, very simple model here. And so it's all based on the fact that work could be defined by a particular force being exerted across a particular distance. And so if your force could be represented by a vector, which makes it really easy to model that, and a distance could be modeled by a vector, to get from point A to point B, then the product of those two should be a way to represent how much work had happened. And again, very, very simple, very, very easy application of the dot product. When you get to more advanced physics classes, you would be talking more about gravity and friction and maybe air resistance and other forces. So again, a very simplistic model. I think it's the adjective I want to use, simplistic model, to help calculate work. And again, all based on the product of 2 vector quantities of a force and a distance. Okay, so What we want to do is create these two vectors, a force vector and a distance vector. And I see a vector here, and it's crazy though. That's the only vector I see, but I'm not even going to use that vector. I'll come back to that in just a second. But the first thing I want to do is actually do the distance vector. That actually is the easier of the two, because it says go from this point up to that point. And so just think about each component. How do you go from 0, 0 to 3, 1? Well, in the x direction, you're going up 3 units. So I would say that's a 3i. And in the y direction, you're going 1. So the vector 3i plus j represents our distance. So I might call that v sub d, our distance vector. Okay, so that's this guy right there. Now we need a work vector, and it does give us a direction of our work vector. I'm going to sneeze here in a minute. I have a feeling. I heard that if you think of pineapple, you're supposed to not sneeze. So we'll see if that worked, because I was thinking pineapples. Okay, so 2i plus 3j. But the problem is if I were to kind of model out that vector, okay, if I go over 2 and up 3, over 2 up 3, just by calling it the vector 2i plus 3j, by choosing the number 2 and choosing the number 3, that gives me a magnitude, if I find the hypotenuse, of 4 plus 9, which is 13. So the square root of 4 plus 9. So I have a magnitude of square root of 13. Again, just by choosing that. And I wanted this direction. I wanted to have a slope that's over 2 up 3, or a slope of 3 over 2. So the problem is if I just pick 2 and 3, its magnitude would inherently be root 13. Well, root 13 is it's almost root 16, so it's almost 4. It's somewhere between 3 and 4, but it's not a force of 8 pounds. And even if I don't know what 8 pounds represents, if I don't understand that as a unit, I know just from a numeric standpoint that 8 is not root 13. Okay, so I need to make this a stronger force, but I still want to keep this a slope of 3 to 2. I just want to continue to extend this until its magnitude is 8. So that's what we're going to do. We're going to scale this vector until we go over enough and up enough that its magnitude is 8, and that's what we need to find. Well, I think the easiest way to do that is to first take that 2i plus 3j, and you scale it down to a unit vector. If I could express that into just 1 unit, and once I know how big 1 unit is, then it's just easy to multiply by 8 pounds to get the required magnitude of 8. And we know how to scale it down to a unit vector. Again, right now, it's root 13. So if I were to just divide by root 13, and then divide this side by root 13, and divide this side by root 13, that would scale that down. So the first thing I'm going to do is I'm going to take this vector and divide out its magnitude to get it to a scale factor of 1. So the unit vector in that direction, so I'll call it maybe vector, oops, I want to go to a different color, maybe this gray color. Vector as a unit would be 2 divided by root 13, I plus 3 divided by root 13j. So this vector is still in the same direction that I want to go. It's just only has a hypotenuse of 1, so it's 1 unit. Okay, now I can take that vector. Since I want a new magnitude of 8, I simply have to multiply that vector by 8. And when you multiply the vector by 8, it's a scale factor. I'm delayed on that color. Scale factor of 8, which means I can just multiply each of the components by 8. And so I could 8 times 2 is 16, 8 times 3 is 24. Still keeps that 3 to 2 ratio with that hypotenuse length of root 13. So now my vector that could represent force, F, would equal 16 over root 13 I plus 24 over root 13 j. Okay, so that's the vector that I want. Same direction, now it has the appropriate magnitude. So then I come back over to my work example, And I know that work is equal to the force, which I had. I'm thinking Star Wars, the force be with you. So 16, I know, really cheesy. It's not going to get any better today. I'm so sorry. 16 over root 13i plus 24 over root 13j. So we're going to take that times our distance vector of 3i plus j. Remember, we learned in a previous video, the way we can represent multiplication of two vectors is a dot product. So we're going to multiply the I components and the j components. And so I have 16 root 13 times 3. No more i's anymore. 16 over root 13 times 3 plus 24 over root 13 times 1. And then, so 16 times 3 is 48, and then 48 plus 24 is, I believe, 72 over root 13. And that would be units of work. At one point, I thought one of the units of work could be represented by foot-pounds. I feel like another unit might be Newton meters, but again, out of my wheelhouse. So I'm just going to leave it as just a scalar value of 72 over root 13. And again, it's just a simplified way to calculate how much work. Okay, so maybe if you want to pause the video and try example 6, and then watch the video and see the solution, that way you can kind of check to see, does this make sense or not? But I will walk through the solution. I'm just going to erase these marks, and then I'll begin. Okay, so just like the last example, I need to find an approximation of work, which means I need a force vector and a distance vector. And I like to find the distance vector first. So going from 0, 0 to 6, 8. So that vector, so v sub d to represent my distance, could be 6i plus 8j. So I know that it's moving to the right 6, up 8. Now, if I wanted to find the magnitude of that, that'd be 10. That's a 3, 4, 5 triangle. That makes me happy. But for now, I just need it to be a distance vector. Okay. Now, let's talk about the direction that they give us in terms of our force. It says I plus 7j. So my force is going to be exerting from some point, go to the right, 1, up 7. So here's my force right now. That is over 1 and up 7. And just inherently by picking 1 and 7, it has a magnitude of the square root of 50. And the square root of 50 is just a little bit bigger than 7, right? Because the square root of 49 would have been 7. And so if I look at, well, what magnitude do I want? I want a magnitude of only 2. So this is too much, right? It's too big. I need to scale it down until its distance or its magnitude is only 2. And again, the easiest way to do that is to take this 1 to 7 ratio. And again, maybe if I drew it a little bit bigger here, so over 1 up 7. So over 1 up 7. And if I think about, well, what is the current magnitude? We said it was square root of 50. I'm going to erase this guy over here just because I want some more space. So right now I know it's the square root of 50. But I want to scale it back down so it's just a distance of 1 to get a unit vector. So I could divide that by root 50. And I'm just scaling this one down to divide by root 50 and scaling this down to divide by root 50. So now I have a unit vector. The unit vector is 1 over root 50 I plus 7 over root 50 j. Right, that represents this value and this value, and its magnitude is 1. Okay, now if I just double that, because I want a vector that has a force of 2 pounds, so if I double that, that would give me the correct slope, like a 7 to 1 ratio, but with the correct magnitude. So 2 times 1 is 2 over root 50, and I know I could simplify root 50. I'm not really concerned just yet about that. And 2 times 7, which is 14 over root 50. J. So there represents the vector of force with the right magnitude in the right direction. So then I'm going to come back over to my formula and say work is equal to force times distance. So then my force vector we said was 2 over root 50 I plus 14 over root 50j. And then we're going from 0, 0 to 6, 8. So we said that was 6i plus 8j. And again, the way we multiply two vectors, we focus on the i's, focus on the j's. So 2 times 6 would be 12 over the square root of 50. No longer need the I. Plus 14 times 8 would be 32. Carry my 3. 112, I believe. 32, carry my 3, 11. Yep. Over the square root of 50. Now, the nice thing, because we have these unit vectors, they'll always have the same denominator. So when I go to add these up, I don't have to find a common denominator. That's 124 divided by the square root of 50. We could simplify that if you would like. The square root of 50 is 25, so it'd be like a 5 root 2. If you wanted to rationalize that and multiply by root 2 over root 2, you certainly could, to get 124 root 2 divided by 5 times 2, which would be 10. But then I realized we have an even number, so I could say, okay, that could be 62 root 2 divided by 5. And again, if I made any arithmetic mistakes, please let me know in the comments. But then that would represent units of work. And again, whether that's foot-pounds or newton meters, I don't care at this point. Again, it's not a physics class. It's just a way that we can apply a dot product. And so really, we're going to see two ways in this chapter we're going to be using dot product. It's going to help us find the angle between vectors, but then I'm also going to use it as a model to multiply vectors that represent certain quantities, and that's going to help us find work. Okay, so I think that's it for this video. So I'm going to work out the example problems, I think on the next page, on the next video. So keep working.